we started to talk about gas exchange. And just to remind you a few things that we finished with during the last class is that the concentration of gas in the solution is directly proportional to its partial pressure above the solution. Remember that? That's one thing that we talked about. Second is that when we talk pretty much the Dalton's law here tells you that the partial pressure of the gas is a measurement of its concentration, right? So the higher the concentration of gas in the mixture, the higher its partial pressure. It means more gas of that sort will be dissolved in the fluid, in this case blood. Okay, and the last thing that we mentioned is that there's different solubility for different gases, and that, I don't know how to regulate it, so we'll just leave it at that, and that with increased temperature, solubility falls and vice versa. Okay? Now let's see how it can be applied. How can we use it when we talk about the gas exchange? So let's take a look at the content of the gas in just the atmosphere and in the alveoli. Okay, you can see that there are several changes between the atmosphere and alveoli. One of them is that partial pressure of oxygen in the alveoli is lower than in the atmosphere. Partial pressure of carbon dioxide is higher. And partial pressure of vapors is higher. Which means that the air in the alveoli, okay, it contains more carbon dioxide, more water vapors, and less oxygen. Okay, it kind of makes sense, right? Because in alveoli there's constant exchange between the air and the blood and the air, right? So oxygen goes back and forth, carbon dioxide goes back and forth. Since carbon dioxide gets out of the blood, its concentration is slightly elevated. So since it's slightly elevated, oxygen concentration is slightly decreased. Okay? So this gives us the partial pressures that those two are the ones that we have to focus on. One for CO2, this one, and one for oxygen. Okay? So these two, we're gonna look at them when we discuss the external respiration. So the exchange, the actual rate, the actual diffusion of gases through the membrane, the respiratory membrane, which is essentially this. So I strike the respiratory membrane. The exchange of gases through the respiratory membrane is influenced by the pressures, of course, the thickness of the membrane, thin, okay, it is thin, so it has a huge surface area, because if you would look at that model of alveoli right there, they're all spheres. It's like a lot of tiny little bubbles, right? Now, what can impede the exchange? So if membrane becomes thick, in case of, for instance, pulmonary edema, or if the surface area decreases in a disease like emphysema. So what happens in emphysema, when you have those alveoli, right, and then walls between adjacent alveoli start to collapse, and instead you have something like that. So obviously this is much less space than something like that. Does that make sense? So when alveolar walls start to be destroyed by inflammation, for example, that decreases the surface, total surface of the respiratory membrane, and decreases the exchange. So external respiration is pretty simple. These are the concentrations of CO2, of oxygen in the vein and oxygen in the alveoli. So obviously, oxygen will go from alveoli to the blood in the capillaries. Does that make sense? So this is the concentration in the oxygen-poor blood. So that's what we get in the end. Oxygen goes to blood from alveoli. On the opposite note, concentration of carbon dioxide in the blood, right here, is higher than concentration of carbon dioxide in the alveoli. Okay? So oxygen will go from the vein, from the blood, from the capillaries into the lungs. Does that make sense? Say again? CO2, sorry, carbon dioxide, of course. You can see this process right here. Thank you for correcting me. You can see this right here. CO2 leaves the blood and enters alveoli. Oxygen goes from alveoli into the blood. Bless you. Does that make sense? So that's external respiration. Now, if you would look at the gradient in the CO2 concentrations, it's not really steep, so 45 to 40, compared to oxygen, which goes from 104 to 40 as well. Okay, so it's much less steep. But remember, we discussed the solubility of different gases. Oxygen is less soluble than CO2. Does that make sense? Oxygen is less soluble. That's why the carbon dioxide exchange, despite not very steep gradient of partial pressures, occurs at the same rate as the oxygen exchange. Does that make sense? Okay? So difference in solubility allows CO2 to diffuse across the membrane faster, despite the fact that the concentration difference is less steep. Now, the exchange happens very, very quick. Okay, you can see that this is the approximate time the blood spends in a capillary, in a pulmonary capillary. It's the time that blood has allotted for it for the gas exchange. That makes sense? So all gas exchange must happen in 0.75 seconds. Turns out that all gas exchange normally at the baseline happens in 0.25 seconds, in 1/3 of that time. What would be the reason for that? Think about the exercise process. When you start to work out, what happens to the blood flow? It increases. So blood flow increases in the systemic circuit, and it also increases in the pulmonary circuit, right? Now, when blood starts to circulate faster in a pulmonary circuit, the time that it spends in a pulmonary capillary goes down from 0.75 to, I don't know, 0.4. seconds. But there's still enough time for the proper gas exchange. Does that make sense? So I have like threefold time reserve for the gas exchange. The perfusion of the alveoli and ventilation of certain areas of the lungs are linked to each other by a so-called perfusion-ventilation coupling, which can be explained in a very easy manner. Now, the major function of the blood is to do what? Yeah, so, yes, deliver oxygen, nutrients. We talk about oxygen here, okay? So deliver oxygen. In the lungs, what does blood do with oxygen? It takes it, picks it up, right? So obviously, you have to direct as much blood as possible to the area with increased oxygen concentration. Does that make sense? That makes sense. So here's the example. You have increased ventilation right here. You see how big alveolus is? A lot of oxygen. So blood vessels will immediately dilate. Blood vessels that lead terminal arterioles will dilate, increasing blood supply to that region. Does that make sense? More blood will flow to the area of the lung that has more oxygen, and that oxygen will be picked up and delivered to the tissues. Make sense? Like people going to on Black Friday, people go to the store which has most doorbusters, right? On the other hand, when ventilation decreases, okay, blood vessels will constrict. Because there is no point of running blood through the alveoli which have very low amount of oxygen. Does that make sense? Now think about the consequences. So this is what we talked about. Oxygen is high, arterioles dilate. Oxygen is low, arterioles constrict. That makes sense so far? Think about the consequences. If you have locally higher concentration of oxygen, blood flow will increase. What will happen to the oxygen concentration in that region? It will decrease, steadily, because blood will start to pick up more oxygen. Does that make sense? Essentially, if in the long term you have some areas of the lungs that are dysfunctional, like have emphysema, have some kind of inflammation, where local concentration, where local ventilation is poor, local blood flow will become poor as well. Right? When you have Radio Shack, nobody goes there. Okay, there's nothing to get in Radio Shack. So it's pretty much like if you have a local Radio Shack in the lungs, there's no customer flow, there's no blood coming over. Okay? Now, ventilation is regulated too, but it's regulated via the carbon dioxide changes. So if certain region of the lungs demonstrates increased CO2 concentration, increased CO2 partial pressure, okay, the bronchioles that lead to that part of the lung will dilate. Do you understand why? When bronchioles dilate, which process will happen faster? Yeah, the respiration, the expiration, the breathing. So when CO2 goes up, which automatically means oxygen goes down, respiratory passages that direct air to that particular part of the lung will become wider, okay? So we can put it this way. CO2 increases, okay? In parentheses, oxygen decreases. Does that make sense so far? Oxygen decreases. That leads to bronchodilation, okay? Ventilation, remember? Pulmonary ventilation. Ventilation increases, CO2 exhaled, oxygen inhaled. Does that make sense? Does that make sense? Okay, good. That's what allows you to get rid of carbon dioxide faster. One thing that I really want you to understand here, I frequently say that we use reductionist approach. We cannot comprehend, and nobody can, the whole picture of human organism at the same time. We can't really see all the processes going at the same time. So when we say, okay, oxygen is high, arterioles dilate, oxygen is low, arterioles constrict, you have to appreciate that this regulation is a constant process. They always dilate, constrict, because gas concentrations fluctuate, okay? Gas pressures fluctuate, okay? So it's a constant process. Any questions on the ventilation, contraction, ventilation, perfusion coupling, sorry. I can promise you there will be a question on that matter, okay? So finally, you've got oxygen in the blood, you've got CO2 out of the blood, and oxygenated blood gets into the tissues. So partial pressure of gases in the tissues is different from partial pressure of gases in the blood. So you can see that oxygen in the blood, its partial pressure is about 100 millimeters of mercury. Oxygen in the tissue is about 40. Oxygen will go from blood to tissue. Does that make sense? Partial pressure of carbon dioxide in the blood is lower than in the tissues. So carbon dioxide go from tissues to blood. Does that make sense? So what you end up with, oxygenated tissue and deoxygenated blood. Again, we use reductionist approach. So if we, I think we compared blood to a truck, like a truck carrying a load. Now, this represents the situation when the truck comes, arrives at its destination and just dumps all load at certain destination. It's not like that. It's more of a like those trucks that throw the salt on the road. When they drive around and they slowly distribute it. Same goes for the blood. As it flows through the tissue, it constantly delivers oxygen. And cells in the tissue, they don't just sit and wait for the next shipment. They constantly use oxygen, so it's a continuous process. We can say that at the arterial end, sorry, let me erase this stuff. We can say that at the arterial end, this is what we have. At the venular end, this is what we get. And from here to here, okay, it's a long process of gas exchange between the blood and tissue. Does that make sense? Good. Because the next thing will involve a heck of physical chemistry. I don't see an excitement. A heck of physical chemistry. We're going to talk about hemoglobin first. mentioned this molecule a bit before. It's protein. So I have 4 chains, okay? Okay. 2 alpha and 2 beta. Each subunit, so 4 subunit, 2 alpha and 2 beta subunits. Each subunit binds 1 heme. So far, you staying with me? Each molecule of heme contains 1 iron and can bind 1 oxygen. Okay? So essentially, think about this. This is simplified version of hemoglobin. So you have alpha, alpha, beta, and beta. Does that make sense? That's oxygen. So without even looking at any further what I'm saying any further, what's the saturation of hemoglobin here? How many possible spaces are occupied? In percentage? 25%. 50. 75. 100. Right? How many molecules of hemoglobin do we have in the blood? Yeah. That's underestimation, I think. More than a lot. Do they all have 4 oxygen molecules? No. Okay? So you have to understand that some of them at a given time may have 4, some of them may have none, some of them 1, 2, 3, and so on and so forth. Is that understood? But you can imagine that in oxygenated blood, almost all of them have 4, right? Almost all molecules carry as many as they can. So when we talk about the saturation of hemoglobin, and we will talk, okay? The saturation of hemoglobin. We talk about average number. Does that make sense? You take all hemoglobin molecules that you have in the blood and you average. Does that make sense? That's why we can have number like 98%. So, molecule of hemoglobin that carries oxygen here is called oxyhemoglobin. The molecule of hemoglobin that doesn't have oxygen on it is called deoxyhemoglobin. Does that make sense? Right? Think about hemoglobin as the truck. Each molecule is an individual car that can carry certain load of goods. Interesting feature about that car is when you load oxygen, car changes its shape, and each next molecule of oxygen becomes easier to add to the hemoglobin. Does that make sense? It's like with alcohol. First time you try a beer, you don't really like it. But as you continue, eventually people start to like it. Okay? Well, most of the people, I don't know. So each subsequent molecule of oxygen binds to hemoglobin molecule easier than the previous one. This is called cooperative binding. Interestingly enough, same goes with unloading. First molecule unloads hard. But as it continues, each next molecule becomes easier and easier to unload. Does that make sense? Okay? Now, we can change the loading and unloading, the rate of loading and unloading, regulating the saturation of hemoglobin, and that allows us to regulate the oxygen delivery to the tissues. We're going to talk a lot about this graph in the future, like future several slides. I know it looks scary, but I'm gonna repeat it multiple times. So this graph, so it's x-axis and y-axis, and here on x-axis is the oxygen in the lungs, or, well, it shouldn't be in the lungs. Let's put it in a different way. Partial pressure of oxygen. And here you have a saturation. Okay? So basically, this graph shows you that higher partial pressure corresponds to the higher saturation. Does that make sense? That's very important idea. So if you have a higher partial pressure of oxygen, say in the alveoli, it means that hemoglobin in the blood will be more saturated. Does that make sense? However, this relationship is not linear. And these curves, which are called hemoglobin dissociation curves, exemplify it. They show that when you increase the oxygen partial pressure, saturation increases rapidly and then kind of stalls. Does that make sense? It also shows that the dynamics of saturation depend on the temperature. Actually, as it turns out, hemoglobin saturation depends not only on the temperature, but also on the pH of the blood, concentration of carbon dioxide, and oxygen. Now, kind of giving you a heads up. Increased temperature in the tissues and decreased blood pH. When would you observe it? It's not a disease state. Lower pH, so acidity and working out. Very good. When you work out, your tissues become warmer and they become more acidic. What they require more also? Oxygen. Okay? So essentially, the oxygen delivery to the tissues that are hot and acidic should increase, and we'll see how it works. So let's look at the hemoglobin dissociation curve in the details. So this is the partial pressure of oxygen. Okay? In which part of the body you're going to find this partial pressure? Oh, similar to that. The high concentration of oxygen. Which body organ? The lungs, right. That's the lungs. This concentration of oxygen, we're going to find it below tissue. Are you following me up until this point? Okay, good. So high in the lungs, low in the tissue. Let's take a glance at the saturation of hemoglobin. In the lungs, for the simplicity, we can say it's 100%. It's not 100, it's 98, but let's say 100%. Okay? So this is your truck being loaded completely. Okay, you see? Completely loaded. And then the blood, loaded with oxygen, goes into the tissue where the partial pressure is 40, as Lily mentioned, and it unloads oxygen from hemoglobin. And let's see what the saturation here. I can tell you that this number is about 75%. So what does that mean? Like in the example of a truck, let's use the truck as an example. So you had 100% loaded truck to the top. You drove it to, I don't know, the warehouse. Did you unload everything? No. Turns out you left most of the load in the truck. You left 75%. 75% is left. 25% unloaded. Does that make sense to you? When I first time saw it, it didn't make sense to me. Why do you want to unload only 1 out of every 3 oxygen molecules in the tissues? I mean, I understand we reach the goal of oxygenation anyway, but we unload only 1. Do you see that? Now let's take a look what happens when pressure changes. So this is lungs, right? This is you hanging out at the sea level on the beach. Okay? Partial pressure of oxygen in the atmospheric air is normal, 760. Saturation, 100%. Does that make sense? Next, you have another person right here who's in the mountains. Oxygen concentration in the mountain air, is it higher or lower? Lower. So partial pressure of oxygen here in the mountains lower than partial pressure of oxygen at the sea level. Let's take a look using that dissociation curve. What happens with oxygen saturation? At this time, it doesn't change much. Look, maybe 1-2%. Does that make sense? One thing that it's not a digression, just a little remark. This curve is empiric. What does that mean, empiric? It was measured. It doesn't come from any laws. It's sort of, it is what it is. Like if somebody would ask you, why do we have four limbs? That's just us. We have 4 limbs, ants have 6. Okay? That's just evolution. We turn out to have 4 limbs. Does that make sense? So this curve was actually measured. It is like this. It exists like this. Why oxygen concentration is 21%? Well, it turned out to be that way. Does that make sense? There's no law of physics that allows you to deduce this curve. It's just, it's the observation. It's observation, yes. It's the fundamental observation. Okay? That's the property of the human body. Inherent property. Does that make sense? Okay, that's a very important thing because one of the questions that I sometimes hear is why this curve looks this way at the higher pressure and it looks this way at the lower pressure. Well, it's just us. Okay. Now, that actually, one of the consequences of that is that at the higher altitude or at the lower altitude, doesn't matter how deep you breathe or how rapidly you breathe, it produces very little increase in binding of oxygen. Because this curve, we will try to continue it above physiological levels. it will become plateaued. Again, going back to the analogy of the truck has certain capacity. And when you loaded it, to the top, no matter how more you're going to pour on it, it's not going to carry anymore, right? Because everything will just spill. Does that make sense?
Isn't that why, like, people that live at high altitude, it's like, to go with that analogy, it's rather than, increasing what you put in the truck, just increase the size of the truck.
Absolutely. Yes. You making more red blood cells, because saturation is slightly lower, but even that stimulates the accumulation of red blood cells. Okay? So they don't try to breathe harder, although your first response when you go to the higher altitude, you breathe harder. When you jog, I did jogging in Colorado. I breathe like I'm carrying, a horse, and it doesn't really help, because you try to close this gap, okay, and increased breathing doesn't really do that much. You can't really elevate the pressure to the levels you used to, but eventually you get adapted. Something like that. Probably for the complete adaptation it requires months, but you can see effects even if you spend a week or two. And you go back to the plains. That's important. You go back to the plains and you just immediately see the effect in terms of the endurance, which is not very long lasting. Now, let's take a look so this is the adaptation to the altitude, So this reflects, even as we go up, okay, the saturation, if we go up moderately, saturation doesn't really decrease that much. So you have that very limited decrease. Now, let's say you go to elevation of 25,000 feet, which is really a lot, okay? So this elevation, oxygen concentration, will be much lower. I don't really know the numbers, but even let's say it's going to be like, 60, okay? So in this case, what's going to be the saturation? 90. This is bad. This is really bad. This is severe hypoxia. People can lose consciousness over that. That's why the climbers, the mountain climbers, when they go to Everest, they actually have to carry the oxygen tanks with them, because they just can't function at this level. Does that make sense? So now let's see the adaptation to the exercise. So this is your normal partial pressure of oxygen in the tissues. And this is saturation of hemoglobin. I'm going to remind you it's 75. So which percentage is being unloaded? 75 left. 25 is being unloaded. 1/4 of all oxygen that your blood carries is actually unloaded into the tissues. Does that make sense? When you start to exercise, let's assume the oxygen partial pressure falls twofold, 20 millimeters of mercury. As we know from observations, saturation of the hemoglobin at this point is at 40%. So how much will be unloaded? 60%, which is called a venous reserve. Okay? So by this venous reserve, by this difference doesn't require you to breathe any harder, actually. Does that make sense? When blood enters tissues that are metabolically active, tissues that are working, cells that actively metabolize stuff, cells that actively do cellular respiration, cells that actively consume oxygen. But the partial pressure of oxygen decreases, it automatically stimulates increased unloading of hemoglobin. Does that make sense? The more oxygen tissue uses, the more oxygen is being unloaded from hemoglobin, which means it doesn't really require that much of an increase in the blood flow. You see what I'm trying to say here? Blood flow will go up, but it's not required. Unloading of hemoglobin increases because oxygen concentration in tissue goes down. Yes. Nutrients. It's a combined response. It's both nutrients, both oxygen. Think about this: when muscles contract, one of the things that happens is that it squishes the blood vessels. So actually blood flow becomes intermittent. So in this case, you have to compensate by increasing the blood flow to the contracting tissues and by increasing unloading. Okay? So now, in sort of very simple way, what will alter the unloading? Sort of counterintuitive. I want to show you how this curve, the hemoglobin saturation curve, changes. Different factor changes, and we're going to talk about CO2 first, carbon dioxide. Okay, so this is the normal hemoglobin saturation curve. Do you follow? Now this one, the purple one, is the curve corresponding to the higher concentration of CO2 or higher acidity. Now let's see what happens at the same oxygen concentration. So if we're going to take 40, okay, let me use the black color, okay, take 40 and this is the unloading at the normal condition. Everybody understood what I just did? No? Okay. No, I just want everybody. So this is partial pressure of oxygen in the tissues. Okay? This is where it crosses the normal curve, the homeostatic, the normal, the stationary phase curve, sort of, when you relax. Okay? And this is how much oxygen is unloaded. Can you remind me the number? 25%. Now let's take a look. Where does it cross the curve that was measured for the higher CO2? Here. Do you see that? This is where it crosses, the purple one. So corresponding unloading will be roughly, roughly 40. So what is the conclusion? Increased carbon dioxide increases unloading. Very good. Does that make sense? Now, we played with numbers now and graphs and all other stuff. Now, let's see what produces increased CO2 in the tissues. Exercise CO2 increases, unloading increases. Does that make sense? Now, in which direction increased CO2 or increased concentration of protons decreased pH, shifted the curve? How would you say it? Just one word. In which direction? Right. Right? It's right over the well. For you, it's right. So curve is shifted to the right if unloading increases, and it shifts to the left if unloading decreases. Does that make sense? Do you want me to slowly repeat it one more time? So if unloading is how much oxygen goes from hemoglobin into the tissues. Does that make sense? Oh, that's what is kept on hemoglobin. You talk about... Wait a minute. You talk about this one? Oh, that oxygen is stuck with hemoglobin. It's there. Only 25. So this to the tissues. Okay? Let me finish the next one. Remember the question. And you will tell me why it is left. What is the physiological importance of having 75% of oxygen stuck with the hemoglobin? Okay? Now wait, think about it. Now, if we look at this picture again, when CO2 goes up or pH goes down, curve shifts to the right. So increased unloading. When CO2 goes down or pH goes up, curve shifts to the left. Decreased unloading. Does that make sense? So far. Now let's take a look at the temperature. With the increased temperature, where does the curve shift? To the right, which means unloading increases. Let's sum it up. What increases unloading? Temperature. CO2. Well, pH decreases. Proton concentration goes up. Those three things are the signatures of what process in the tissue? Yeah, cell respiration, active metabolism. Does that make sense? When tissues are metabolically active, they produce a lot of CO2, a lot of acid, and decrease oxygen actually concentration. Now, does that make sense? We'll get back to your question, no worries. Now, what actually changes the unloading? Each of those parameters, temperature, acidity, they change. Where is that? I want to highlight it. The affinity of hemoglobin for oxygen. What does the word affinity mean? Attractiveness, yes. So when hemoglobin at the higher temperature becomes less attractive to oxygen, it becomes easier for oxygen to leave hemoglobin, to go from hemoglobin to tissues. Does that make sense? Like, it becomes, the dissociation becomes faster. Okay? That makes sense. This It's called a Bohr effect. When oxygen unloading increases in the tissues that actively use oxygen. Does that make sense? The more certain tissue uses oxygen, the more it produces those metabolic factors that increase oxygen unloading from the blood. Going back to Lily's question. In the resting state, what is the purpose of having that venous reserve here? What is the purpose of having a venous reserve? Okay, yeah, well, if the demand increases, it's not necessarily demand. Well, one thing is, of course, when demand increases, your blood can rapidly react to what? Lowered oxygen, partial pressure oxygen concentration in tissues, right? Can you imagine the situation, which is not normal, I warn you. Can you imagine the situation when, even without exercise, the oxygen concentration in tissues progressively decline? Okay, something that blocks, we'll get to that. It's carbon monoxide is slightly different. It works at a different level. Okay, no oxygen supply, no ventilation. Someone is being suffocated. You see? Now, when there is no oxygen delivery to the lungs, zero, you have that amount of oxygen in your blood. It's a depot, oxygen depot that allows you to survive for about a minute or two without respiration. It's a time that brain is fully functional without oxygen getting into the lungs. And then it goes into the hypoxia and starts to die. Does that make sense? When breathing ceases, when somebody gets completely suffocated, okay, it's about a minute or two when oxygen bound to hemoglobin allows brain to function. That's the evolutionary purpose, the physiological purpose of that depot. Right? Now, lack of unloading of oxygen in tissues, lack of supply, is called hypoxia. Hypoxia causes cyanosis, accumulation of deoxyhemoglobin, which is more bluish, just gives the blue color, blue shade to the blood. That's why people who are oxygen deprived are cyanotic. We discussed that. Cyanosis is a symptom. So it can come from anemia, lack of iron, for example, lack of red blood cells in general. Ischemia, lack of blood flow. If you will try to do that for a very long time, the arm becomes, bluish, sort of. It's better to do with some sort of a rubber band or something. Histotoxic hypoxia. So metabolic poisons prevent cells from using oxygen. That's what Francesca was referring to. Do you know of any metabolic poisons like that? Huh? Oh, you can look at one of the words. So cyanosis. Cyanide. It was named for cyanide. I don't actually know which one was named for what. Okay. The chemical formula is very, very simple actually. So this is the potassium cyanide. Potassium CN. Okay, so it's a metabolic poison that blocks cell respiration. Now, what do you think? How will it change the oxygen concentration in the blood?
Or increase it.
Increase. Why?
Because they're not using the oxygen for cellular respiration.
Much simpler reason. You're right, but much simpler reason.
Can't unload the oxygen.
Much simpler reason. Your cells not using oxygen. So you feel like you're being suffocated. What you gonna try to do? Breathe. That's it. You're gonna hyperventilate. It's not gonna help. Okay? There was a famous case when there was cyanide poisoning of Tylenol in Chicago. And several people died of it. Still not, it's been investigated. Nobody was found to be guilty of that. So it's deliberate poisoning of Tylenol bottles. Hypoxemic ventilation problems. Okay, like in case of emphysema, you can see people with emphysema or chronic obstructive pulmonary disease. They often have cyanotic, kind of bluish hue of their lips because of a lot of blood flow. You can just notice it there. And carbon monoxide poisoning. That's what you were referring to. So this thing works at slightly different level. So carbon monoxide, if we'll try to write down the equation for it, it's going to be like this. Sorry, not CO2, of course. So CO plus hemoglobin forms carboxyhemoglobin. Now, carbon monoxide here, okay, it binds to the same place as oxygen. Okay, so they compete. Oxygen and carbon monoxide compete for hemoglobin. Does that make sense? Compete for the same place. Carbon monoxide is much better. Has much higher affinity to hemoglobin than oxygen. So when people start to inhale carbon monoxide, it starts to substitute oxygen in the blood, and there's very little chance for oxygen to kick it out back. Does that make sense? So it's like, imagine that, I don't know, me and Dwayne Johnson would compete for the same seat in a theater. I would stand no chance once he takes it, right? Same here. Now, interestingly enough, first symptom of carbon monoxide poisoning is bright red skin. Because carboxyhemoglobin, this compound, okay, has a very bright red color. So people with monoxide poisoning have like bright red cheeks, bright red palms. And the treatment, of course, the first and foremost is to pull out and bring into the fresh air. Because when you start to increase oxygen concentration, it gives oxygen a little edge. Does that make sense? But as far as I know, you gotta give them the pure oxygen for treatment to increase the concentration of oxygen in the lungs. Okay. And actually, this gas has no smell, so it complicates things a little. Okay, you know what? We're going to take a break before the CO2 transport because it's an entire different story. Okay, before we go to the break, the exam is going to be in a week from now. It's going to cover only